the continuation of mechanical properties of solids, that what is Hooke's law? In previous class we have explained about what is elastic limit. The elastic limit, which means what we said, the maximum stress within which the body regain its original size and shape after the removal of deforming force, which is called elastic limit, right? Hooke's law, what it states that? Hooke's law states that within the elastic limit, the stress which is directly proportional to the strain, right? So the stress which is directly proportional to strain, which is equal to constant, we have taken constant, the proportionality constant, as the modulus of elasticity or the quotient of elasticity. So we can say the modulus of elasticity, which is equal to stress by strain, right? Since the strain is a pure number, the units of the constant are the same as those of stress, that is Newton per meter square. Got it? Stress and strain curve, we can see that. See, the stress and the strain curve will give and show for the metal wire which is gradually being loaded, and this helps to understand the tensile strength of a given material. See the graphical representation of a stress strain curve for a ductile material. We can take a ductile material. It is like a metal wire, right? The initial part, if you noted, means OA of the graph is a straight line that indicates that the stress is directly proportional to strain. So up to point A, we can say that the Hooke's law is obeyed. The point A, we can call it as the proportional limit. Okay. So the point A is the proportional limit. Until the point A, the Hooke's law is obeyed. And after point A, the stress is not proportional to strain. See, notice that curved portion of AB. The curved portion of AB is obtained through that it is not obeyed. That means that particular part after the A, the Hooke's law is not obeyed by the particular material. And however, if the load is removed at any point between O and B, the curve is retraced along BAO. Check it. And the wire attains its original length. See, the portion OB of the graph, we can call it as, it is an elastic region because it is regaining its original length. Got it? And the point B, we can call it as, it is an elastic limit or yield point of the particular material. And the corresponding stress, we can call it as yield strength. Right? Now, you can notice beyond the point B, the strain is increased more rapidly than the stress. If the load is removed at the point C, the wire does not come back to the original length, but trace dashed line CE. Even on reducing the stress to 0, we can't get the strain equal to OE. It's left in the wire. The material now is said to be the permanent set. It is plastic nature. It is a permanent set. Okay. So the phase of the stress strain curve is not retraced. It is elastic hysteresis area. And furtherly, if increases the load beyond C, what will happen? It produces a large increase in strain or the length in the wire. The stress correspondingly, what will happen? Highest point. So we can say that it is the ultimate strength or the tensile strength. So beyond the point, additional strain is produced even if the wire is unloaded and finally the wire breaks in the fracture point. We call it as E. So this region between B to E, the length of the wire on increasing even without any additional load. See, this region only we can call it as a plastic region. Right. And that particular plastic region of the material is plastic flow that we can't deform it. So through the graphical representation, you may understand how the stress strain curve obeying the Hooke's law in particular area and where it is the elastic limit, that means the B point, and where the permanent set, the elastic hysteresis, and where that is the plastic region. Got it, children? Now we'll see the modulus of elasticity. See, the modulus of elasticity, what we said, that is the ratio between the stress and strain. This we got it from Hooke's law, right? So the modulus of elasticity, we can say the ratio of stress corresponding to the strain within the elastic region, the elastic limit. That is very important. So these are all three different types, that is Young's modulus, bulk modulus and modulus of rigidity. One by one we can see, right? So first Young's modulus. See, the Young's modulus of elasticity, you may see the diagram. Within the elastic limit, the ratio of longitudinal stress to the longitudinal strain is called Young's modulus of material of the wire. See, suppose you have taken a wire of length L and the cross-section area A. You have given some change in the length, increasing length under some force. We have given some force acting along the length L. Now we can take the Young's modulus, which is equal to longitudinal stress by longitudinal strain. That is F by A. Longitudinal stress means what? That is F by A whole divided by longitudinal strain is del L by L. F by A longitudinal stress, which means tensile stress. F by A. Longitudinal strain means change in the length to the original length. So del L by L. So we can take it and simplify it. We will get Y, which is equal to F by A into L by del L. Got it? So the unit of the Young's modulus, Newton per meter square, or we can say Pascal. And its CGS dyne per centimeter square. What is bulk modulus? See, within the elastic limit, the ratio of normal stress to the volumetric strain. Normal stress or a longitudinal stress to the volumetric strain. So we can say bulk modulus B or K also we can say, which is equal to normal stress by volumetric strain. Normal stress is what? F by A whole divided by volumetric strain is del V by V. So we can say K, which is equal to minus of F by A into V by del V, or we can say PV by del V. See here, the P, which is equal to F by A, that is the normal pressure. The negative sign which shows that the volume is decreases within the increase in stress. Right? And also here we have to explain one more term, that is compressibility. Because here volumetric strain which is happening, there what we said, that is compression in the volume. Strain in the volume. In the same way we can say the compressibility, which is nothing but the reciprocal of bulk modulus of the material. 1 by K. Right. Shear modulus or modulus of rigidity. So it is defined as the ratio of tangential stress to the shear strain. See the diagram. We can take the rectangular block Because lower face is fixed and a tangential force F which is applied over its upper face. So, an equal and opposite force F which comes into play on its lower fixed face also. Is it right? We must agree with that. The two equal and opposite forces from the two sides, it will form a couple. If it forms a couple means what will happen? It will exert a torque. So, the couple shears a block into its upper face through the distance. It's varying like AA dash. It is changing. Let's AB we can take it DC. So, that is equal to L. So, if you have taken the angle AB A dash, check it AB A dash, that is equal to theta. That is only change in the length, right? So, the tangential stress which is equal to F by A. So, the shear strain theta which is approximately equal to the tan theta we have taken. So, tan angle we have taken means AA dash by AB. So, that is equal to del L by L, right? So, the modulus of rigidity, what we said? The tangential stress by shearing strain. So, eta which is equal to F by A whole divided by theta. So, that is equal to F by A theta. So, that is equal to F by A into L by del L. So, this we can say that modulus of rigidity or shear modulus. That is the ratio of tangential stress to the shear strain. Got it? Thank you, students.